All materials, based on their composition, what they're made of, their length, their dimensions, have certain natural frequencies that they want to vibrate at. If you can activate one of those natural frequencies, you can create a standing wave, but it only occurs at those certain frequencies. It's called a standing wave because the pattern seems to stand still. You can create waves at any sort of frequency, but if it's sort of random or if it doesn't hit one of those natural frequencies, the pattern's going to be all over the place. But when you hit one of these natural frequencies, the pattern just repeats over and over. It stands still in the medium. This occurs when a wave interferes with its own reflection. You keep sending waves down to one end and they reflect back, and if you match the frequency of them coming back towards you, you can create constructive interference in certain locations and destructive interference in other locations. Let's look at standing waves on a string. Let's imagine we have a string stretched out between two people. Let's assume it's fixed on both ends. You're holding one end, the other person's holding the other end, fixed in place. This dashed line represents the string, or the slinky, or whatever it is, all stretched out in its equilibrium position, no waves in it. It's going to be of a length capital L. The first standing wave you can create would look something like this. This point is going to oscillate back and forth, almost like a jump rope. And so this dashed line represents it sometime later. Just imagine going back and forth and back and forth. The whole thing's going back and forth, back and forth, back and forth, back and forth. This end here, where maybe you're holding, is what's called a node. It's a position of no movement. While you're still creating some waves from that location, they pretty much cancel each other out. So it's a position of destructive interference. You send the waves down, they reflect back, and when they interfere over here, they destroy each other. This position over here, where someone else is holding, or the other end that's fixed in place, is also a position of destructive interference. There are two nodes here. This point in the middle that moves the most, well, it's called the antinode. That's a position of most movement. That means that the waves are combining in a constructive way. So there's constructive interference here, creating a large amplitude. This is known as the first harmonic. Those of you in music will start to recognize some of the vocabulary we use when referring to standing waves. This is the lowest frequency that can cause the standing wave to occur in this medium, so it's called the fundamental, or F1. If you double the frequency, you're going to get the next standing wave, or the second harmonic. So again, the string, or the slinky, wherever the medium is the same length. So we want to try to draw it the same length. The ends are lined up here. This is what the second standing wave looks like. We have two of these positions of large constructive interference. There are two antinodes, and then 1, 2, 3 nodes. You're holding, someone else is holding. This point in the middle is also a point of destructive interference. The wave is causing the medium to oscillate back and forth, back and forth. So this point here goes back and forth, back and forth. This point goes here, goes back and forth, back and forth. We're trying to capture that as a static image. This is the second harmonic, and this frequency is twice the fundamental. If you triple the original frequency, you get the third standing wave. Again, let's assume that the medium is the same length side to side. This is what the third standing wave looks like. 3 of these antinodes, shown here as well. 1, 2, 3, 4 nodes. This is the third harmonic. F3 equals 3 times the original, 3 times the fundamental frequency. Now let's look at it in terms of the length of the medium compared to the wavelength. So on this first harmonic, we can see we only go up to crest and back to equilibrium. This is not a full cycle, right? There's actually half a cycle. The rest of the cycle will be somewhere over here, we can imagine, if the medium were to continue. So in this case, the length is just half the wavelength of the wave itself. There's only half a cycle shown there. It should be pretty easy to see in the second harmonic. We have the full cycle. We go up to crest, down to trough, and then back. And if this were a traveling wave, it would just repeat itself. And so we have the full wavelength that's here, or 2 halves of the wavelength in this whole length of the slinky. I'm writing it this way because we're going to start to see a pattern emerging. In the third harmonic, we have 1.5 cycles, so the length is 3 halves of the wavelength. Now we see the pattern emerging that every single time we go to another harmonic, the next standing wave has an extra half a cycle or half a wavelength fitting in the same amount of space. So let's start to put all this together in some equations. We saw that the frequency of whichever standing wave we're looking at was just an integer multiple of the fundamental frequency. We can write that as Fn, the frequency of the nth harmonic, is n, the number of the harmonic, times the fundamental frequency. So n is the harmonic number. F sub n is the frequency of the nth harmonic, the first harmonic, the second harmonic, the third harmonic. And F1 is the fundamental frequency, the lowest frequency that will cause standing waves to occur in the medium. In terms of the wavelength, we could write that the length of the string, or the slinky, whatever the medium was n over 2 times lambda, the harmonic number causing n half wavelengths to occur in that same length. We combine this with v equals f lambda, we can get the speed in there and the frequency. So we relate it all to the frequency of the harmonic. Lambda equals V over F. And now we're just going to substitute lambda equals V over F into here. So we have L equals N over 2 times V over Fn. We're now writing this as the frequency of the nth harmonic. We're writing it this way because you have control over the frequency. The length of the medium doesn't change, but you can shake it at different frequencies. So we're going to solve this for F sub n. So F sub n equals NV over 2L. We can box that in as the equation for the frequency of the nth harmonic for standing waves on a string fixed on both ends. And now we can just officially say that L is the length of the string. We showed it in our pictures before, but we haven't really defined it in our equations.